Welcome to Friday lecture. This is actually take two. So, for those of you that were here for the live lecture, this is going to be a little different. As you remember, we had some technical snafus, and I froze a number of times. So, I'm going to quickly kind of rehash what we covered in lecture. Yeah, so if you weren't here, then you'll be none the wiser. Yeah, let's jump in. I want to quickly bring us, so a couple things I want to cover today. We want to look at the T table and get a better feel for how to use this to find our T values. I want to spend some time looking at polling. So we'll actually pull up 538 and just play around on the site a little bit just to get a sense as to where we can find some of these polls, being that we are now under 4 days, 3 days, how does time work, a few days from the end of the election, and so you may find use or interest in looking in at some of these sites. So we'll do that briefly, and then I want to walk through just one more polling example and some of the things that we can do with polls. To put in kind of frame of reference why we're dealing with this T distribution and this kind of cumbersome T table. I'm gonna let's see. Yep. So just to refresh, and I know we've covered this a few times, but what are we after here? And again, we're trying to get a hold of how we can apply our sampling to the population, and how we can express what we think the best guess is out there for us, a population value. So a lot of times thus far, we've been dealing with this idea that we don't know the population mean. And we can take a sample and use our X bar as a way to express roughly what we think the mean of the population might be. Okay, and I've been using this kind of maybe not fully mathematically correct concept that kind of the roughly equal. Okay, and that's what we're trying to express, is that we think we have a value that might be close, or is probably close to the population mean. It's our best guess, but there is uncertainty there. And so how do we express that uncertainty numerically? And that's really what we're after here in Chapter 9, is building that confidence interval. And so we have built those confidence intervals, pulling from our understanding of the z-score, right? And we've made this conversion, so square root of n. So we won't walk all the way through all of that, but we've come up with, this is where I have a little more space, x bar plus or minus z, and then sigma, and over the square root of n. Okay, so that was our confidence interval. But of course, this is under the assumption that we know sigma. And when that breaks down, when we don't know sigma, which again is quite frequent, we have to fix that, right? We have to have some way to express something. We have to put something in place of sigma, and so we've said we can also take the sample standard deviation. And again, you can roughly think of it as, and apologies to math majors, I know I'm fudging the what you study, but roughly we're trying to say S is pretty good at predicting sigma as well, but we need to build in some uncertainty there. So that's where we turn to the T distribution rather than the Z. So loosely, or kind of broad picture, what are we trying to do? We're trying to push out the confidence interval, right? And so when we think about what we've done over here with the Z distribution, or the Z value, oftentimes what we say, we've taken a 95% confidence interval. This means that we are plugging in 1.96 into this equation. Now, let's say sigma is, let's say the true sigma is 7. Okay, the population standard deviation is 7. But let's consider a scenario where we don't know that. So we're playing with S. So we have to put S in here. We take a sample standard deviation, it might be really close to 7. It might be a little bit more. It might be a little bit less. If we take a sample standard deviation and it's less than 7, if it happens to be lower, then what we're going to get for a confidence interval is going to be smaller than it otherwise would, right? So let's say we plug in 6.3. And if we were to just build it based on the z-score, we would have a tighter window than we otherwise would with the true population standard deviation. So this creates a problem in that we're being overconfident about our window. And so the way we counteract that isn't to change S. And I want to be clear, this is just one potential sample. We could have 7.3 or 8.1. Right? We could get a sample standard deviation that's larger than the population standard deviation. Not a big issue. We're underconfident, and that's not as big of a concern, right? If we give too wide of a window, that's fine. We don't want to express too small of a window. And so to counteract this, what we're going to do is we're going to still use S, but we're going to change this value. We're going to change from the Z to the T. And really the whole point for the T distribution, especially in our case here, is to push out that confidence interval. Right, so we have some, if we want to think about the window being kind of a range around that X bar, what we don't want to have happen is, in some sense, this smaller one, those should be even lengths. That's going to annoy me. We don't want to have the S lead us to too tight of a window. And so what we do is we push it back out with the T distribution and get it back at least, to where we were, and in fact will be slightly wider than with the Z distribution. So that's kind of what we're after with that. And the way we do that is we employ a new number here, and that number is going to tend to be larger. Okay, for any if we're in the 95% confidence interval, the numbers are for T is going to be larger than 1.96. If we're dealing in 90%, remember the 90%, if you recall, for the Z is 1.645, the numbers are going to be larger than 1.645. Now, the confusing part, and what will be confusing when we turn to the table, is that there is a new T distribution for every sample size. And the reason for that, again, is we get a better feel for where sigma is when we have a larger sample size. Okay, S does a better job, or we're more sure that we're close to the right value of sigma when we have a larger sample size. So we don't have to push out as far on the T. Okay, and so you can review those other videos, but we've talked about how the T distribution gets tighter as we go. That's horribly drawn. Something like that, right? It starts to tighten in, and so we use a smaller and smaller T value, which is going to approach 1.96 kind of in the limit. So that's kind of the setup of why we need to go to the T distribution. One last thing, remember the Z table is all about connecting Z and a percentage. Okay, same thing for the T distribution. We can go to the T table and flip from a percentage to a T, right? So we're going to do that with like 95%. The only other thing is that we have to kind of run it through our sample size. Now, one last little confusing part is that we don't strictly look up the sample size. We look up something called the degrees of freedom. And in our case here is n-1. Now, we'll have more to say about degrees of freedom in the next couple chapters when we start tweaking that more. But for now, as we learn the T-table, you can associate it as n-1. So if we have a sample size of 25, we look up degrees of freedom 24. So, yeah, I'm going to pull up the T-table. one little tiny window of it, or one corner of it. Give me a second to get this rerouted. Now, this is going to feel a little bit different than the Z table. It's organized slightly different. That should be pretty good. And so let's take a look. So the first thing to note is that there's a lot going on here. So let's focus in. We're going to use this t-distribution a number of times in the next few chapters, and we are going to use it for some of these other things, 1 and 2 tailed tests. But for now, we're going to focus just on the confidence interval. Okay, and so what that means is we scroll down into the table, you can ignore kind of this whole chunk of stuff. Okay, what we are interested in is this top level, the confidence intervals. Now, so that's the first thing. This is where we're going to find what confidence interval do you want? 80, 90, 95, 98, 99, 99.9. Those are kind of the most common. Again, you could have a different confidence interval, but these are by far the most common. And so you'll want to, as a researcher or a data analyst, you would pick the confidence interval you think is necessary. When you turn to answer your assignment questions, you'll often be given, calculate the 98th percentile, or sorry, 98th confidence interval. 98% confidence interval. That would be the terminology. And so in that case, you would look with the column or underneath the column of 98%. So each of these columns is, well, that's not going to help. Each of these columns is associated with a different confidence level. So, yeah. So let's take a look at it now. Next thing to note is that there's there's all this stuff over here, and then there's a bunch of stuff off beyond my arm over there. This is all one long table. It's just chunked into different parts. So let's take a look at the degrees of freedom. We said we're going to look at degrees of freedom, which is n-1. So for instance, if we had a sample size of 50, we would look at the value 49 degrees of freedom. And so as we scroll down, we get to 35, and then it starts back up here at the top with 36 and continues on. Okay, so just getting our heads wrapped around where the table goes, and then we jump down to the second page. It just jumps right back in at 71. Okay, so you can think of it as one big long table with only 7 columns, I guess, with this. But and then we jump back over. We can get to 89, and then it starts to skip a little bit. You could, if you had a sample of 167, you could look up 166 exactly in a using an online tool. And then as in the last part, you can see if I'm out of the way enough. When we get to by the time the sample size is 200, so let's look in here at this 95% confidence level. By the time we're at a sample of 200, or degrees of freedom of 200, so 201 in our sample, we're really close to that 1.96. Okay, so there's not a lot of, we don't have to push out very far in our confidence level to feel good about this, because with a sample of 201, we feel pretty good that we have a good sense as to where sigma actually is. S is going to be very close to sigma. And in fact, the last row in infinity, if we take this to the extreme, it becomes the Z distribution. Okay, here are those common, the ones you're familiar with. I'm in the way of the 99, or that's 98. There. Yeah, so that's where we say that T distribution eventually becomes, or basically becomes, the Z distribution. That's what we're talking about. So let's look up, I think we said sample of 50. So where is degrees of freedom 49? Let's scroll back up here. Again, let's say we're thinking 95%. So we come down and we find degrees of freedom 49, and we get 2.01. So that's the value we plug in instead of that 1.96. It's going to just push it out just a tad. We're building in a little bit of leeway for us not being exactly certain about where sigma is. Again, with a sample of 50, we feel pretty confident, but we do want that little extra degree of uncertainty. Now, thinking about moving around in this table, this also kind of makes sense, right? As our sample size goes down, let's say our sample instead of 50 was 40. We'd kind of scroll back up here to, highlight that, scroll back up to degrees of freedom 39. And we've added a little more uncertainty. That t value that we plug in there is going to be a little bigger, and so our confidence interval is going to be a little wider. Okay, nothing drastic here, but I'm building in a little extra. And as we scroll back up, it starts to increase. Let me go back down. Here's 35. You follow it up. Nothing really drastic, but when you start to have sample sizes below 10, it starts to balloon quite quickly. Okay, and that should make sense. We're trying to use sigma, or use S to estimate sigma, and we haven't taken a very large sample size. Okay, jumping back to our degrees of freedom 49. Similarly, if we thought about 95% confidence interval, and we said, all right, this time we're going to do only 90% confidence, that's going to be a tighter window, right? We're less certain. You can think of it as kind of less uncertainty. We're building in less uncertainty because we're just saying 90% confidence. So that, is a smaller number, 1.677. So again, that you can think of that in reference to the 1.645 of the Z. Okay. So that's kind of how we move around the t-table. Again, you'll get more familiar with it as we go, especially because we're going to be jumping back into it again with this 1 and 2 tail test. Okay, so we have a percent that we're interested in. We can find a value just like we could with the Z. It's just a different kind of flow. All right, so I wanted to then jump over and look at, we're going to look at some polling. And specifically, that's not what I wanted. There we go. We're going to look at some polling. We're going to look at just where you can find certain polls. So one of the quickest places to find recent polls is on 538.com. You have to spell out 538, otherwise it doesn't. Takes you to some other site. So 538.com, you might be able to just see up there. And it does take a little time. You got to find the right place. Let's go to politics. And usually there's, here we can jump into national polls. That'll get us started. You can see all kinds of presidential polling. We've talked about that. We've ran some examples of that in class. So let's go back up and look more generally about, or more specifically, to Minnesota. So maybe we're interested in, where are the M's? Minnesota. And we have a poll from the U.S. Senate race. So Tina Smith is up for re-election. Amy Klobuchar is not, but Smith is against Jason Lewis. And there are a few polls out. Generally, you'll see more polling with tighter races. It makes more sense to get a better feel for that. So we do have some out. Now, yeah, you can start to see, we talked the other day about kind of grading pollsters and trying to get a feel for how well they do at that type of making sure their polls or their samples adequately reflect the population, doing some good random sampling, accounting for people not responding and those types of things. So 538 goes through that process for us. They generally do a pretty good job of grading out the polls. So it's always good to bear in mind, you might put a little more weight behind a poll with an A versus a C- down here. Yeah, and we can see certain things. So we can see the sample size. That might be very small on your screen, I realize. Zoom in a little bit. So we can see the sample size of 650. Again, as we talked about, you're going to see a lot of polls with that sample size in the 650 to 1,000 in that range, and not a lot much beyond that. Remember, the return on that just isn't that good, right? You have to really start to increase quickly if you want to get down to that kind of 1% margin of error. But yeah, we can see other. Let's just see what's going on in Minnesota. You can see presidential. You can see, so typically, again, there's not a lot of polling, not around election time, although, so Governor Walz is not up for re-election and not for a number of years. You can see polls from, when he was elected. There was a poll, St. Cloud State put out a poll June 5th. So you will see polls pop up every once in a while, especially after major events. So obviously here in June 5th, this is soon after civil unrest and here in Minnesota, and so people were interested in kind of what is the support of major politicians after those types of events. So those typically do come out, or it's not uncommon to see polling after major events. But more typically, you'll see it as elections approach. And so you can look up the House races. A little less frequent here. There's not a lot of polling out here. And yeah, so you can check out the other states. What was I was trying to. Yeah, here we go. Okay, so you can also go and take a peek at their pollster ratings and get a little better feel for that. And these are unsorted, so you can see some of the stuff going on. They go all the way down to F. 538 bans them from some of their deeper. They're trying to model kind of full, the whole race overall, and so they'll ban certain ones that perform quite poorly. They give you a sense as to mean their bias. So some polls tend to favor one candidate versus the other, one party versus the other, and so that's kind of reported here. And then you can get a sense as to races called correctly. Now, it's important to note here that this is none of these are 100%, and they shouldn't expect to be, and in fact, we shouldn't expect them to, because that's not the point of a poll, is not to determine with 100% certainty who's going to win the race, and in fact, that would be impossible. And so there's going to be cases where a poll shows one candidate in front, and the other candidate wins. And most notably, you'll remember this from 2016, actually, 538, Nate Silver, the head, they showed, Trump losing in the polls, but with a certain percent likelihood to win, and of course Trump won, and that in and of itself is not a scar upon a poll or a polling system or a prediction system. So when we expect, it's similar to just one single confidence interval. If we have a 95% confidence interval, we do expect that to not to be right every time. Okay, there are that percent chance. It's not exactly the confidence interval, right? Confidence interval is doing it. If you did it 100 times, 95 of them would contain the true value. In a similar sense, if you make a lot of predictions, some of them are supposed to, or it should be that some of them end up wrong, right? You have a certain percent chance to have it right, and so there is a chance of having it wrong. So that's just, they don't always get it right, and we shouldn't expect them to. So you can see the method here. So and you can read more about that definitions here if you're curious. But they span from online polls to phone calls, cell phone calls, so on. There's starting to be text surveys done. Okay, so with that in mind, let's talk through one more time about kind of how we can produce polls, or how we can think about polls. Let me jump back. So you'll notice a lot of these don't sum to 100%. And that's because we don't force people to respond, or either say that they've decided they can be undecided, they can vote for. Some of these will have more than 2 candidates, such as here. Although that one is, well, we got the 99% there, but so far we've only kind of covered the cleaner versions where they sum to 100%. The math isn't wildly different for these cases, but we can maybe turn more to that later on in the semester. For now, we're going to stick with kind of the nice, clean calculations. So let's do that. Let's run through one more example. If I can pull this up, and let's base it kind of around a Smith-Lewis race. There we go. So for ease, I think that they used an N. I think it might have been 649, but I'm going to use 650 because it seems easier. I'm going to write that back up in the corner where I thought I was. Okay, so we've called 650 people, and we'll use a similar spread, or pretty similar. Well, let's say Smith and Lewis, and we found out that 340 to 310. Keep it nice and clean here, and just verify I'm doing the math right. So that leads us to a P. Remember, P is our estimate for pi, the proportion that are going to do something or have a successful trial. So I think in class we let the favorite be the X, but it works either direction. So let's say Lewis is X here. That's going to give us, you can double check this, but I think it's 0.477 roughly. And so this is going to be 0.523. Is that true? So because that is 310 divided by 650, that becomes the 0.477. So our best guess for Lewis is that he'll win 47.7%. Again, I'm kind of fudging this, that it'll probably be more. The last poll said 42 to 45. I'm keeping that same kind of rough window. Yeah. So that's all well and good. We have a good guess, but we want to build in that uncertainty. And again, remember, we're going to use P plus or minus, a similar format to our Z calculation, or our confidence interval. And we're going to do P 1 minus P over N here. Okay, so let's go ahead and crunch that. And we say, so 0.477 plus or minus 1.96. Let's stick with the 95% confidence interval. And then this is 0.477 and 0.523 over 650. Okay, and while I figure out what that exactly is, I'm using these rounded values, so could be slightly different. And so I get 0.00038. Let's take a square root of that, and we get 1.96, and then this is a 0.0196. We'll call it 0.0196. And let's finish that out. 0.96. So I get 0.477 plus or minus 0.0384. That's good enough there. So we would say, we'd report this as Smith 52%, 52.3%, Lewis 47.7%, plus or minus 3.8%. Okay, so we now have a way to kind of express the uncertainty in this polling as well. Now, we can take it one step further and actually talk about how likely do we think it is that Lewis wins the race. And this is actually why I wanted to stick with the clean example relative to 50%. In a couple more chapters, we'll be able to do this calculation comparing the two groups, even if they're not. We'll be able to factor in both Smith and Lewis's values here. But for now, let's just think about what's the chance that Lewis gets over 50%. So we can think of this in terms of we have a guess. If the true value is of Lewis's, if we can think of the value of Lewis at 47.7 and think about how likely it is that he actually gets to 50%, this is a normal distribution. Okay, so we can think of it in terms of here's 47.7, and we want to know how likely it is that he gets 50 or beyond. Okay, if he goes the other direction, if it's lower than 47.7, he's not winning anyway. So we're going to focus in just on this one direction. And so really what we're after is, we can think of it as 50 minus 47.7. We should probably put that in decimals. Let me just jump to decimals. So 0.50 minus 0.477. And then we do want to put that, right? We're in a normal distribution. We want to put that in terms of a spread here. And we can do that. Let's see. We can do that by using what we've calculated in the past here. So we have well, let's calculate the top here. So 0.5 minus 0.477 is 0.023, and we are going to use the bottom we've already calculated as kind of the standard deviation of this distribution is going to be our 0.0196. Okay, taking that from kind of what this calculation is. So we get 0.023 divided by 0.0196, and we're going to get 0.0196. We get about 1.17. Okay, and that is it's behind me. Let me just move out of the way. We get a z. This is a z-score of 1.17. If Lewis were to get 50% of the vote, if he's truly polling at 47.7%, that would be 1.17 standard deviations above where he's polling at, and so we can treat that as a z-score. And if we look that up, flip that back up, 1.17, or 1.1, let's go over to 7, we get 0.3790. We get 0.3790, which of course is not exactly what we're after. That is this area. And so we need to subtract it from 0.5. Okay, and so that leaves us with, what is that, 0.121? So about a 12.1% chance that Lewis wins the race. Okay, that's what our polling would show. In this case, with kind of this polling results that we've made up, but roughly associated with the current polling. And so that's a rough estimate as to maybe Lewis's chances right now, given that polling. Now, this is just based off of one poll. So if you're back on 538, oftentimes what they're doing is they're taking into account multiple polls and kind of the mixing those all together with some a little more advanced kind of statistical methods or ways to encounter or capture the results from more than one poll. So they may show slightly different percentages, but it's probably not wildly off from this. Yeah, so hopefully that gives you a feel for the polling, where to find it. You can also check out Real Clear Politics. They have kind of pretty much every poll that comes out there as well, and so you can follow that along the way. You can get, if you're curious about which kind of results to watch election night. You can find that on 538 as well. They do a pretty good job of knowing, okay, that you should pay attention to kind of these, middle results in these kind of swing states or toss-up states. Yeah. And as we were just seeing, here's the Senate. We were just looking at one of these individual results. Or polls, not results, and you can see. So actually we can pull this up. I don't know if you can see it there, but they have a 93% chance for Tina Smith to win, which is not wildly off. We had Lewis at 12% based on that single poll that we fudged. Yeah, and in fact, you can see if you look in there, they have a forecasted vote share as well, which is again drawing on multiple polls. Yeah, you can play around with that and become more informed before the hecticness of next week. Yeah, we'll leave it at that. Again, I'm around this weekend. You have your exam coming up, remember, so dig into that coming this week. And again, that's going to be due Tuesday by noon, so that if on the off chance that you haven't gotten to the polls, you have all the rest of the day free, where you're not going to be working on this. You're going to be out there working on this. So, yeah, we'll leave it there, and we'll talk to you soon.